तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome to lecture number 48 on our ongoing series on mechanical measurements. Towards the end of the last lecture, we were actually talking about vibration measurement, and in particular we were talking about the laser Doppler accelerometer. We will resume from there, and in the current lecture we would try to cover the following topics. If we go to the slide, we will be able to see what we are going to do. We will discuss fully the laser Doppler accelerometer. Then we will also look at a new instrument which is called the fiber optic accelerometer, which I have taken from recent literature. Then we will switch over to the measurement of torque, speed and power, which are relevant for characterizing engines, power sources and so on. So that will be the final topic which I am going to look at today. So we will revert back to the laser Doppler accelerometer, which is shown here in the schematic. So as we were explaining in the last lecture, we have a source of radiation in the form of laser. The beam is allowed to be incident on the target, which is the vibrating member whose vibration we would like to study. That means the target is moving in and out, as it is shown here by these arrows, and the light is reflected from this. If one can attach a small reflecting tape onto the target so that the light will be reflected back. And we have a beam splitter which makes the beam take a 90-degree turn, and it is incident on a second beam splitter, and this beam splitter will split into two parts, one which goes towards this mirror and the other one which goes towards this mirror. So as we were explaining in the last lecture, this length is much larger or much different from this length. So there is a path difference between the path B and path A. This path imbalance is inserted or introduced wantonly, and that is given by delta L. So again the reflected light from this mirror as well as this mirror, again they combine together and are incident on the photodetector. So what happens in this particular instrument is that the laser light which is reflected from the target, which is oscillating, is combined together after splitting it into two parts, one which travels a longer path and the other one which travels a shorter path, the path difference being delta L. So because of this path difference, a certain phase difference is introduced, and that is the one which will help us to find out what is the target vibration of the target. So let us look at that in more detail by looking at the following expression. So we are now combining two beams, two light beams, and we are using a laser light because it gives you very highly coherent beam with a fixed frequency or wavelength. Okay, these two light beams, one, if I call it the B and A, there is a path difference which has been introduced delta L. which has been introduced intentionally. So, the signal at the detector if I am thinking of the frequency to be omega or the circular frequency to be omega, this is the oscillation of the target. So, the target is oscillating or vibrating. For the present we can assume it is a constant omega. Of course, if the omega is, if it consists of several different waves put together, we can take a Fourier component and work on that. So, I am looking at one such component, oscillation of the target at omega, and now what we get at the signal is a combination of two beams B and A. The frequency, there will be a beat frequency, because when we combine two beams with a phase difference, we will get a beat frequency when we combine them, and that is what we are going to look at that. So, it is proportional to, it can be shown it is proportional to 2 by lambda multiplied by the first beam or the second beam ut minus delta L by C. This is what we are talking about. So, there is a, because of the path difference, there is a time difference here. This is time difference. Of course, remember that the velocity of the beam of light is the same as the speed of light and it is very high value. Therefore, we need delta L by C will usually be a small quantity. It is not a large number we are talking about. So, in a way it is like combining two beams or two quantities here with a small time difference, and we know from our ideas of differentiation that the difference between two signals taken with a small time difference will contain the velocity. If the quantity we are talking about is the velocity, the difference will be acceleration, because there is a small time difference. If you take the two signals, it will be proportional to the acceleration. Actually, we can show that, but I am trying to cut short by just mentioning it, so that we can directly go to the expression. So, what we can do is we can assume that u is a sinusoidal given by, let us say, a sin omega t, and ut minus delta L by C will be a sin omega into t minus L by C, delta L by C. So, we are now taking the difference between these two sinusoidal functions, and I can use the trigonometric relations, and it will give you sine of, it is something like this, sin A minus sin B will give you sin A plus B by 2 sin A minus B by 2. So, I can combine these two. This difference will be the difference between these two quantities, and will be nothing but there is a component with A plus B by 2, the other one A minus B by 2. This A plus B by 2 will be omega t plus omega t minus delta L by C, because this is very small, this is simply omega t itself. So, you see that this will contain, I am sorry, here we made a mistake, this is cos A plus B and this will be like omega t itself approximately, and this is the one which contains the difference in A and B, the two quantities A and B. Therefore, this will be proportional to this delta L by C. Okay. So, let us look at this result. So, we will, and because this is sine of a small quantity, we can also use sin theta is equal to theta formula, and this will simply become omega delta L by C. This A minus B by 2 becomes omega delta L by C. Therefore, the signal at the detector will vary according to this form, omega delta L by C cos omega t. And this omega cos omega t, if you see here, is nothing but du by dt. Du by dt is a omega. So, if you just multiply, the factor a is not very important, just the amplitude. So, you see that this will be proportional to acceleration. So, delta L by C multiplied by acceleration. So, you see that the laser Doppler instrument, in this particular case, the signal is proportional to the acceleration, and the acceleration is the output of the instrument. So, that is one type of instrument which we can think of, where we are using the vibration to generate the acceleration signal through the optical mixing of two beams by introducing a certain delta L path difference. And this path difference can be introduced nowadays with a simple way of doing it, is to take a coil of fiber optic fiber, and the length can be suitably adjusted, so that you get a sizable factor delta L by C, and therefore, we can do that very easily. The light passes through the optical fiber, goes to the other end, gets reflected from the mirror, comes back through the same fiber, and then is mixed with the other beam. The two beams can be mixed together with a large path length required. Delta L can be large, because C is a very large quantity. So, that is one way of measuring the vibration or the vibration acceleration. And the second one I am going to look at with a very simple idea. This is called a fiber optic accelerometer. I will just explain physically what is being done here, and let us look at the things we have. We have a cantilever fiber. It is a very small diameter fiber, where in this case you can see it is 18.4 millimeters long and 240 micrometers diameter. So, it is a very small fiber. Why do I use a fiber? Because I can send a light beam through the fiber. So, from the laser light from the left side, it goes through the fiber and exits from this side. So, if the cantilever beam is perfectly stationary, that is, there is no movement, the beam which enters here will come straight down on this side. Okay? So, it comes axially out of the cantilever fiber. At the downward side, I have got two optical fibers to collect the light which is coming from the left. These two fibers are kept with a small difference of spatially different positions, and you can see these are the two. So, what will happen is, if the laser beam is coming through this, a part of the laser light will enter through the 1 and the other part will enter through 2, and if it is symmetrically arranged with respect to this fiber, half will come here and half will come here, and therefore, the intensity of laser light coming through this and this will be exactly equal. Okay, we can adjust the to start with. When the cantilever fiber is perfectly stationary, then these two will give you same output. The signal will be the same. Now, imagine a certain vibration being imparted to this fiber. This fiber is now going to sense the vibration which we want to measure. So, what will happen is, if I subject it to vibration, the free end will start going up and down. So, if the free end goes down most down, it will communicate more to the lower fiber and less to the top fiber. Okay. Therefore, the signal, if you take these two laser output from these two and look at them, they will oscillate, they will also change in time. So, the displacement of this will create a difference between these two signals through this, and therefore, whatever information I have here in terms of the frequency of vibration, that will also be the frequency of the vibrational, or the frequency at which this signal will oscillate. Okay. and that is the basis for this particular method, and it is a very simple instrument. This whole thing can be a very small enclosure with the cantilever fiber being attached here, and two fibers are going out. They can be attached to suitable attachment here, and this laser, these two fibers can be very long, so that you can make the measurement far away from this particular accelerometer. The accelerometer is very small. The point is, if the frequency of vibration which is impressed on the cantilever fiber is much smaller than the natural frequency of the fiber itself, then it responds very well to the input signal. So, the displacement will be proportional to the input if the natural frequency of the cantilever fiber is much larger than the frequency at which the vibration is taking place, and therefore it will respond to the acceleration signal, and what you get here will be proportional to the acceleration, and that is what we would like to measure in this case. And let me just give some of the figures which discuss the specifications for this particular instrument, which is given in the paper which I have cited there. So, the frequency range for this instrument is about 0.2 hertz. The particular example which I have taken from the paper, the one which I have constructed, about 140 hertz, and sensitivity, as usual, it is given in terms of the output voltage for a given acceleration. Therefore, volts per G or volts per meter per second square. Either one of them can be given. In this particular case, the value quoted is about 700 millivolts per meter per second square. This is the sensitivity of the instrument. Highly linear. That is also another important feature of this particular instrument. So, to just recapitulate what we have done in the last two lectures, we have tried to cover as many ways of measuring the vibration related quantities like vibration frequency, vibrational amplitude, and the acceleration because of vibration. These are the quantities we have highlighted. So, that completes in one sense one area of measurement which we encounter in mechanical engineering, and we will now move on to another important area, which is the last area I am going to consider in this course of lectures, and that is measurement of torque. Why do we measure torque? Torque is measured because we want to measure the output, mechanical output of an engine or a power source, whatever we are interested in. For example, we may want to know the rating of a motor. So, all these cases we need to measure the torque. So, the torque itself can be measured by various ways. For example, we can use a brake arrangement, and if you remember from your thermodynamics and applied thermodynamics courses, we usually talk about the brake horsepower or brake power output. So, what is this brake power output? We will see in a little while from now. We can also measure the torque by allowing the engine to run a generator or drive a generator, and the generator is generating electrical current with a certain voltage. Now, I can load the engine, load the generator by connecting it to a set of resistances which will dissipate the energy in the form of heat. Okay. So, I convert the mechanical power to electrical power, and the electrical power is dissipated, and the more I dissipate the electrical power, the more load it will bring on the engine, and therefore, the engine load can be changed. And as the engine load changes, we would like to find out what is the power developed and what are the characteristics. For example, I may be interested in finding out how much fuel it is consuming for a certain output. So, I have to measure the fuel input, the amount of fuel which is consumed, and find out what is the power, and then I will be able to relate these two quantities. So, one method is to load electrically an engine with which drives the generator, and the generator is loaded electrically to give a load. In the case of brake arrangement, it is a mechanical loading. In the case of a generator which is being run, it is the electrical loading which is done. We can also we can measure the torque directly by using a brake arrangement, or we could make, I will discuss one or two other ways of doing it also, or we can measure the shear stress on the shaft as it rotates, and from the shear stress I can find out what is the corresponding torque, which are possible. And if I want to measure the speed, in most cases I will be interested in the rotational speed. It can be measured either by a mechanical device called a tachometer or a speedometer, or I can use a non-contact optical RPM meter. Both these we are going to discuss. So let us look at the kind of things which we can do. For example, we have a brake drum dynamometer, which is a very simple instrument. So what we have done is we have a rigid frame, and this is the brake drum, which is driven by the shaft. The shaft is driven by the engine, which I want to test. So on the brake drum I have got either a belt or a rope, which can go round several times. It is not necessary to have just going once, it can go round several times, and it is attached firmly to the rigid frame on the left side here, and with a spring balance. On the right side I have a loading screw, so that I can increase or decrease the tension by loading screw by turning the screw. So you can load the thing. So what will happen in the case of brake drum dynamometer is that because of the friction between the brake drum and that is why it is called the brake. In a brake, it is a friction which is going to come into play. So the friction between the drum and the rope or the belt is going to make the the tension here different from this. This will be higher than this. Okay, it is rotating like this. This is at a higher. This is a higher the tension. This lower tension. Therefore, there is a difference in force. This force is different from this force. That multiplied by this radius of the brake drum actually gives you the torque which is being applied on the engine. So the engine torque is directly measured by the difference between these two spring balance readings multiplied by the radius of the drum. As simple as that. This is one way of doing it. The another way of doing it is actually to use what is called a brake, a prony brake, in which instead of using an arrangement like this and two spring balances, we can actually have a brake riding on the brake drum, and it will be resting against a platform balance, and it will press on it. The reaction from the balance will be measured by directly from the balance reading. And you remember we have already seen a platform balance earlier. So it measures the force, and that force multiplied with the lever arm will directly give you the torque. So the other ways of measuring this, the thing is to measure the stresses in a shaft in torsion. Before I come to that, let me take a look at one more way of doing it, which I will discuss on the board. For example, if I have, let us say this is a generator, and this is the rotor, this is the stator. Generally, of course, the stator will be fixed to the ground, but in this arrangement what we will do is we will allow the stator also to float. So this is the rotor, this is the stator. It is floating because it is mounted on two bearings at the two ends, so that it is floating. So this is free to, if this is rotating, if the rotor rotates, this is also free to rotate. But what we will do is we will attach some kind of an arm to it, and then put it against, or I can do the following also. I can put a force measuring force balance here. So if this rotates, this is also tend to rotate, and therefore there will be a force, and the tendency to rotate is balanced by the force which is acting here, and therefore this is a floating design. So the generator in which the stator floats, and it transmits the force or the torque onto this arm, and this force which you measure here multiplied by this distance. So, we will call it, if this is F, torque is F into R. So, this is one way of measuring. So, these are purely mechanical way of measuring the torque directly by measuring the force and the momentum, corresponding momentum, and then the product of these two is going to give you the torque. The other method which I am going to discuss is the one which uses the following arrangement. So, we know that if you have a shaft which is in torsion, if it is in torsion, there is a shear stress. As if you draw the shear stress diagram, it is like this on the surface of the shaft, and if you draw the corresponding principal stresses, they are at 45 degrees. You can see here that this is at 45 degree to the axis, and this is also at 45 degrees, and you also will notice that along this, these two principal stresses are tensile, while these two are compressive. There are two compressive stresses in this direction, the tensile stress in this direction, and these are all equal. In pure shear, when you have a shaft in shear, in fact, you can draw the Mohr circle, which is familiar to from your applied mechanics. You can see that the tau and the sigma and minus sigma, this is the Mohr circle, and these are the two principal stresses. And you can immediately see what we can do. Suppose we are able to place in this direction, and in this direction if we place two load cells, they will respond to this will respond to the tensile shear, tensile strain, and this will respond to the compressive strain. So, the two of them, this will be reducing the length of the load cell, this will be increasing the length of the load cell, and therefore, you are going to have a difference between these two will be able to give you a large enough signal. So, let us see how that can be done. So, and also you notice that these two sigma values are similar and the same value as the tau value. Tau, sigma, they have the same magnitude in this particular case of pure shear. So, imagine this shaft to be the shaft of the engine, which is driving the either the generator or it is connected to a brake. The brake, you need not measure anything towards the brake side. Now, I am measuring everything on the shaft itself. The advantage of this is this can be done, this can be permanently attached to the shaft, and you can do the measurement without any problem. It does not involve too much of manipulation as in the other case, where you need a external measuring device, a force balance, and things like that. So, let us look at the way this particular thing works. So, the magnitude of the shear stress or the principal stress on the surface is given by this formula, tau equal to sigma equal to T into R by J. T is the torque applied, R is the radius of the shaft, J is the moment of inertia of the shaft, and J is actually given by pi R to the power of 4 by 2. So, all I have to do is substitute here. So, if I know the value of R, if I measure sigma or tau, because this is proportional to the load cell reading which I am going to get, because I am going to use a load cell to measure that, I can actually get T equal to sigma j divided by R, and that is how we measure the torque. Okay, let us look at the way we are going to do that. So, for measuring the sigma or the tau indirectly, what we can do is we can measure by mounting two strain gauges perpendicular to each other and aligned with the directions of the principal stresses. That means, if you remember, the principal stresses are now at 45 degrees to the shaft axis, and therefore, these two strain gauges must be aligned at 45 degrees with respect to the axis, and the two strain elements can be placed on opposite arms of a bridge, because one of them is in tension, the other one is in compression. So, the change of the resistance on both the arms will help in enhancing the signal. So, you can see how it is going to happen. If I look at the strain gauge attached here, this is the shaft. I have got 1 and 3 and 2 and 4. There are 2, and you can see here 4 and 2, 3 and 1. They are on the opposite sides. I have arranged 1 and 2 on this side, 3 and 4 on this side. So, two strain gauges on this side, and on the other side the other 2 strain gauges are attached. This I have taken from a manufacturer's detail. The diagram is taken from this particular website vishay.com. They are the manufacturers of such items, and you can see that I have arranged 2 on this side and 2 on that side, and how they are connected you can see. 1 and 3 are on the opposite arms of the bridge, 2 and 4 are on the other opposite arms of the bridge. Therefore, the signal here is bigger than if I had only one of them, for example, because in principle I can measure the sigma by just attaching one of them at 45 degrees. The idea of putting them in this particular arrangement is to get a larger signal, and in this case I have got 2, 4 and 2 and 1 and 3 are on the opposite sides of the bridge, and as we already have seen when we were discussing pressure transducers and so on, we have already seen how to analyze such a system, and we know that the signal is now decided by it is the sum of the, it is in fact proportional to 4 times the 2 times the sigma, because these two are going to magnify that, and this will be another 2 times. So, it will be proportional to 4 times the sigma. So, you get a large advantage. So, having discussed the measurement of torque, let us look at the measurement of speed. When I am talking about speed, I am talking about the rotational speed of a shaft or rotational speed of an engine. And before we take a look at that, let me just describe why it is important. Why do we require this? So, if I am interested in determining the power developed or supplied by an engine or a prime mover which is under test, how do we do that? The basic idea is to measure the power as a product of torque and the rotational speed. So, we are now thinking in terms of measuring the torque separately and the rotational speed separately. So, 2 separate measurements. Of course, it is also possible that one may be able to measure the power directly. For example, we have already talked about a generator being connected to the engine. So, we will just look at how it can be done. We have the engine or the power is connected to the generator, and it is supplying a load, and power is dissipated here. So, in fact, it is perfectly logical to find out what is the power which is dissipated and directly related to the engine power. Of course, the problem is that there may be some efficiency involved. To the extent that the efficiency of the generator and the coupling and so on is not known or has uncertainty, that will be affecting the power measurement in this direct measurement. So, in the case of direct measurement, even though it is possible, the power dissipated through the load can be directly related to the power generated from the engine if we know the efficiency of the intervening items. So, in this case the generator efficiency and then the coupling efficiency, there may be friction and other losses and so on. So, those are the problems which make it difficult to use this method. Even though for rough measurement it is perfectly logical to make the measurement in this particular form. Or for example, if an engine is running a water pump for example, and if we can measure the output of the pump in terms of the flow rate or the mass flow rate of the water, and we know the head through which it is being pumped, there is another way of finding out what is the power output. So, that also gives you power output. Of course, there again the same problem will come, what is the pump efficiency and then what is the efficiency or what are the losses in the intervening, for example lubricate losses due to friction and so on. So, those are the problems which will come into the picture, but for a rough estimate it is possible to do that, and in many cases that may be sufficient. But what we are now talking about is when you want to do very accurate work and you want to measure, it looks like the only possibility is to measure the torque and the rotational speed separately. So, we have already seen how to measure the torque, what are the different methods which are available for measuring the torque, and now let us look at the rotational speed. We will take a look at one or two different ways of doing it, and that is what we were trying to look at on the slide. So, we have two types of arrangements. We can have a mechanical speedometer, and that is schematically shown here. So, let me just describe how we are going to do that. You will be surprised that it is again a electrical setup. So, the rotation of the drive shaft through gear mechanism will rotate this shaft here. Okay, this shaft is rotated by this is what I want to measure, the rotation speed. This is now connected to whatever instrument, whatever engine or source whose rotation speed I want to measure. This is going to relate to that one. It may be either directly equal to that or it may be a fraction of that, because you can have a gear train doing that. And let us see what are the components in that one. We have this is the heart of the speedometer. We have a magnet, and this is the magnet which is surrounded by a speed cup, or this can be the rotating magnet and this could be the flange. So, what happens when you rotate a magnet by connecting it to the shaft here is that the speed cup, this flange will tend to follow the magnet, because it is going to be it is going to be facing or experiencing a varying magnetic field, and because of that this will tend to rotate, and the rotation is actually prevented by connecting it to a spring. So, it has to it will react to the changes in the magnetic field, but restrained by the spring. Therefore, it will take up a certain position of equilibrium where the torque applied by the spring is equal to the torque which is generated by the varying magnetic field, because of the magnetic cup which is rotating over that. Okay. So, how does it come about? It comes about because this flange, the eddy currents will be generated, and the eddy currents will be dissipated through that in the form of heat, and therefore, it is going to experience a torque. So, actually we are converting a rotation, which is what we want to measure, to a torque, and this torque is balanced by a spring, and the pointer here will indicate the speed directly. So, this is a mechanical speedometer which is found in most automobiles and other two wheelers and so on. This is the simple instrument, and it contains a permanent magnet, and the flange which is rotating inside is going to generate the torque, and which is restrained by the spring, and you are going to have a pointer which indicates the speed directly. So, the second method which is going to be discussed is slightly different. This is a non-contact RPM meter. In fact, there are many variations of this. The one which I have shown here is only one such thing, and I will describe one or two more on the board. So, what does it contain? It contains the rotating shaft which is connected to the engine or whatever whose rotational speed I want to measure, and there is a wheel. This is the wheel with holes in it. In this case, I have shown two holes at 180 degrees apart. There can be more holes or there can be only one hole depending on the particular design. I have a light emitting diode which is shown here, and opposite this is the photodetector which is shown here. So, this is the important thing, a light emitting diode or a source of light and a photodetector which will respond to the light which is falling on it. And you can immediately see what is happening. When the shaft rotates, sometimes the hole will be in front of the detector or in between the LED and the detector, and sometimes the hole will be away, in which case there will be no communication between these two. So, essentially what we are doing is the communication between the light leaving the light emitting diode and the photodetector is blocked when the hole is not in front of it, and it is open or it is communicated when the hole comes in front of that. Okay, let us look at what is going to happen. Suppose I look at the signal from the photodetector. The photodetector will show a signal something like this. So, if I look at the photodetector, let us assume that it indicates, it gives a electrical output. So, we will make a simple diagram. So, when the hole is in front of this is the output, and this is blocked, and again when the hole comes in front of the detector you get the signal, and you see again a block and so on. So, this is the waveform showing how it is going to change. So, you see that the period of this, if there is only one hole, this will be one revolution. If there is only one hole at 360 degrees, that is, you have an arrangement like this, you have only one hole. So, whenever it comes in between the photodiode and the LED, it will give you a signal. Suppose I have two of them. So, this is 1 and 2. So, this will correspond to 1, this will correspond to 2, this will correspond to half revolution. So, if you measure the time taken from here to here, we will call it as t, then this t will be either equal to 1 revolution. So, time taken for 1 revolution, or it could be half a revolution, or if I have 4 of them, you can see that you can now get a signal. Every time a hole comes in front of it, you are going to get a small blip or an output, and the rest of the time it is going to be 0, and therefore, it is like actually the number of times the hole is coming in between the light emitting diode and the photodetector. So, the time here can be either related to the 1 revolution or half revolution or a quarter revolution and so on. Therefore, we can see that the time here is per revolution, t is related to per revolution. So, suppose you get let us say 1 second in 1 revolution, you can immediately see what is the RPM, because RPM, the 1 minute will correspond to 60 seconds will be 1 minute, and therefore, there will be 60 revolution. Okay. So, this just gives you a direct relationship between the period or t, or the period between two of these and the revolution. So, this gives you directly t is directly related to RPM. Of course, the factor will depend on whether you are going to have 1 hole or 2 holes and so on and so forth. So, there is a conversion factor which depends on the amount of time t here. So, t per RPM, t corresponds to some revolutions per minute depending on because we are measuring every time in the case of a single hole 2 pi or 1 revolution correspond to that time, and if it is 2 holes it will correspond to half a revolution, because every half revolution it will come in front of that. So, this is one way of measuring the RPM. And let us look at another one, which is also a very interesting method. It is called a stroboscopic measurement. So, I will explain the principle of that. Stroboscope is nothing but a source of light that can be switched on and off at any frequency. So, it is on for a small period and it is off again on. So, if you look at the, in this case, the source of light comes like this. This is on, off, on, off, and so on. Suppose I do the following. Suppose I have a wheel on which I have put a small marker. This is a marker. Okay, you have a wheel which is rotating and you have a marker. Suppose I have the stroboscopic light incident on the place where the marker is present. Okay. Suppose I illuminate it, I illuminate with the stroboscope. Suppose the stroboscope frequency is different from the frequency which the marker this is rotating. Sometimes you will see the marker, sometimes you will not see the marker, correct. So, if strobe frequency not equal to rotational frequency, can we stop and again start? I think. So, if the strobe frequency and the rotational speed are not related to each other, the marker will sometimes be seen and sometimes you will not see the marker. In other words, it will appear as though the marker is moving. Okay. Sometimes you see the marker, sometimes you do not see. Suppose this frequency is the same as the rotational frequency. So, every time the light comes on, the marker is in the same position. So, what will happen is that if the strobe frequency is equal to the rotational frequency, exactly equal to it, then marker appears stationary. Of course, the observation is made by the operator. So, you have the strobe in your hand and illuminate it and hold it against the marker and then keep on changing the frequency of the strobe. There is a dial and you change the dial so that you increase the frequency. You start from a low value and keep on increasing. At some particular value of the strobe frequency, which of course is calibrated and the dial will show you what is the frequency, you will see that the marker appears fixed. That means that the strobe frequency and the frequency with which the marker is coming to that particular place, they are exactly the same, and therefore, you can immediately see that this frequency and the frequency of the marker coming. If there is a single marker, it will come once every revolution, just like the hole coming in between the LED and the photodetector. Here the marker is doing the same job. The marker is coming back to the same location, and the marker's location, if it appears to be fixed, there is no shifting of the marker, it looks stationary, then you know that the strobe frequency and the rotational frequency are the same, and therefore, the RPM can be directly related to each other. But the problem is the following. Suppose we will go back to the same figure. Suppose if the marker comes after every 2 revolutions in the same position, if it comes. Even then, for example, if the strobe frequency is double the rotational frequency of the shaft, okay, if it is double, then also it will appear fixed, okay, because every 2 times the strobe will go twice and then it will be again, because our eye will not be able to follow that. It is just because we are using eye as the device. So, what will happen is that it can so happen that if the strobe frequency is a multiple of the rotational frequency of the shaft also, there will be a stationary appearance of stationary marker. So, that is the problem. Therefore, the one good way of doing that is to start from a lower frequency and go up, so that you will, the first time you get a match, that is the correct speed. Or if you do the following, if you vary the strobe frequency, it will appear to be stationary at one particular value, again at another value, and so on. You can look at the ratios of these. So, that will tell us something about whether it is the fundamental or the higher speed or the higher speed, and so on and so forth. Therefore, the only thing is we have to be careful about, care is required to identify the lowest frequency at which the match will come. The marker appears stationary or fixed. So, this is one way of measuring the rotational speed. So, we have actually discussed in fact 3 methods. One was the speedometer, which is based on the rotating magnet principle. The second one was the photodiode pickup, and the photodiode LED pickup is now commercially available in the form of a unit along with its electronics. So, it does not require too much of effort to set it up. You do not have to buy each item separately and so on. It is available as a unit and you can buy it and then set it up. Of course, the advantage of the speedometer, handheld speedometer, is a mechanical instrument. There is nothing to go wrong and it is very easy to use it. That is also okay. But if you are going to use the handheld speedometer, it requires some arrangement on the shaft, and therefore, that is not many times it is not desirable. Therefore, normally nowadays what is the best method which is useful is the one which consists of the LED and the photodetector. And let us look at the reason why these measurements are important. This will be the last part of the discussion here. So, why measure these quantities? Already we have mentioned a few reasons for it. One is, of course, in drawing specifications. For an engine, for example. So, what are the things we would like to do or we have to do? One is we have to measure the brake power. Next, we have to measure the fuel input. So, what does the fuel input say? It gives you the amount of fuel in terms of energy per unit time, which is again a input power. So, if you look at the engine as a transducer or a converter, what it is doing is it taking input power in the form of internal energy in the fuel or chemical energy, potential energy in the fuel, it is converting it to brake power, and therefore, normally what we do is we define an efficiency or brake efficiency, or sometimes we also call it the brake thermal efficiency. So, which is usually given in terms of mechanical brake power output, because the brake power output is a mechanical output. You are running the engine against a load, a mechanical load. Therefore, it is a mechanical power output which we are talking about, divided by the input power in the form of the chemical energy in the fuel. This is the, so this will be the most important quantity for our specification of an engine. And of course, there are other things also. What are the, for example, we would like to know what is the range of speeds at which it can be operated, and also the characteristics of the engine. For example, I would like to, for example, do the following: efficiency, this quantity versus speed. I should be able to draw curves which give the efficiency versus speed, so that I will know what is the, how the engine is behaving, or the, in this case I have taken the example of an engine, it could be any prime mover. So, you will get some curve like this, some numbers like this. So, you will immediately see that this data can be analyzed by using the methods we have discussed earlier, by curve fitting. Therefore, in any activity which involves measurement, including the characterization of engine, we can talk in terms of the fitting the curve, and then talking about the variations. For example, you can see these are the error bars. You can see here there are errors here. We can find out what is the variance of the eta, or the standard deviation of the eta which we are measuring, and therefore, it contains a lot of wealth of information, and that is possible by making measurements as we have discussed here. So, with this actually we are coming to an end as far as the various measurable quantities are concerned. In the next 2 lectures, which are going to be our completing this course of lectures, we will look at some issues which we have not touched upon earlier, specifically data analysis, data gathering, data management. So, we will look at that in the next 2 lectures. Thank you.